Hello everyone. In this video we're going to talk about how to get the idle control open loop settings correct. I won't be covering how to wire idle motors to the ECU or how to configure the outputs to do that because we've done that in another video. Now, just like getting the fuel mixture right, getting the idle control right starts off with having the basic map correct and then allowing the closed loop to do the final last bit. So let's look at the basic factors that go into setting the open loop idle. Firstly, let's find where we can see the idle effort in the software. You can see it on the gauges window next to the RPM. The RPM field shows the current RPM, the target RPM and the idle effort, which could be a duty cycle or a percentage of the number of steps or a percentage of the maximum throttle authority on an electronic throttle engine. But it's expressed as a percentage so that it's consistent between all those variations. And of course you can add it to a monitor window if you want to. Now first of all, let's consider the cranking condition. In this situation, the ECU holds the idle valve at 100% effort, so fully open, which gives the most air available to start the engine so that it starts easily. So in other words, with the engine stopped, or if the engine's less than the cranking RPM threshold, say 300 RPM or whatever, then you'll see the idle effort will be 100% the whole time. So next, let's consider what happens when the engine actually fires. After the engine fires, the ECU is in the running as opposed to the cranking mode. So in this mode, the ECU calculates the idle effort from the following factors: the base idle effort table, or duty cycle table, which is a function of coolant temperature, post-crank idle effort, additional idle effort for electrical loads and air conditioning, thermofans, power steering and that sort of thing, and also closed loop corrections. Now initially we're going to turn the closed loop corrections off, and this enables us to see what the actual settings are doing rather than how it's behaving after the ECU's tried to fix it. Now if we're setting up idle control from scratch, what we should do is set all the idle up values for thermofan, electrical loads and so on to 0, and set the base idle effort table first of all. So this is best done with the engine starting from cold. So firstly, set the target idle speed against coolant temperature to where it needs to be. Now, for most port injected engines, the RPM when it's cold needs to be slightly higher than the normal operating RPM because otherwise the fuel falls out of suspension, ends up on the runner walls and doesn't burn. Now, once you start the engine, you can then adjust the base idle duty to get the correct idle speed as the engine warms up, so you can do that at each temperature point then. Then you can extrapolate the ones from the top and from the bottom, so to fill out the table. Now the other way that you can do it is you can enable closed loop control, and then once you've set up closed loop control and it's working correctly, you can just look at the value once it's actually stabilized on the target and then write that into the base idle effort table. Now that's a lot easier, but you need to have the closed loop setup working first of all. Now next you need to set up the idle up for the loads. So the procedure for this is to adjust the additional effort so that the target idle speed is still maintained when the load is applied, or you can allow the closed loop idle to correct the idle effort, get the difference between once it's corrected versus before the load was applied, and then put that number into the idle up value. Now this procedure is also described in more detail in the air conditioning video and also in the thermofan video. Now there are some electrical loads that the ECU will only know about because of external inputs that come into the ECU. So often there'll be a headlight input going into the ECU and a power steering switch input going into the ECU, maybe a blower fan input, that sort of thing. Now generally these are either switches which pull to ground when they're being activated. For example, a power steering pressure switch. So in this case, just connect that pin to the switch and select it as being power steering and leave it as active low, not active high. So that way it'll be triggered when that switch pulls that pin to ground. So you just have to select a digital input that you're not using to do this. Now another example is a headlight input. Generally with headlight inputs, the input actually goes up to 12 volts when the headlights are switched on. So that again needs to go into a digital input on the ECU. And then you can select that as electrical load 1, for example, but set it as active high instead of active low. And then it'll come on when the headlights turn on. So when any of these electrical inputs or the power steering or the air conditioner inputs are active, the ECU will increase the target idle RPM to be the new target when on value in the idle up page. Now if this value is below the target idle speed, then it won't change the target idle speed at all. So it's a maximum function if you like. Now the extra duty alternator function is for cars where the ECU is able to see the alternator field current. So how much current the alternator is delivering or how much load it's putting on the engine therefore. So for example, if the alternator regulator is built into the ECU rather than the alternator, so for example on the NB and later MX-5s, on the Dodge SRT4, on the Mazda RX-8 and so on, and the 86 FRS BRZ, then for the plug and play ECUs we actually have the alternator control provides an input to the ECU, and you can use that to control the idle effort. So to configure this you need to select a minimum and maximum voltage for that input based on the range of operation of the alternator. So normally you'd set 1 as being the condition where the engine's hot and no thermofans on, no air conditioners on, no blowers on, no headlights are on, the battery's charged and all that sort of thing. And you'd select the other end being when all the electrical loads are on at once. Headlights, high beam, demister, blah 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 blah. Then you'd set the minimum idle effort to be 0, and you'd select the maximum idle effort to be the amount of idle effort that you need to deal with all these electrical loads on the car. And then the ECU will scale it linearly in between those 2 points. And in practice this works really well and much better than having a digital input to tell you whether an input's on or off. Now the final function that I want to talk about is the post-crank idler. This is a table with coolant temperature on one axis and time on the other, so time after cranking. So t equals 0 is actually the point where the engine first fires, and then 5, for example, is 5 seconds after it started, and so on. The maximum time that you can do this for is 5 minutes, so 300 seconds after the engine starts. But in practice, if you need that long, then you're probably doing something wrong. So just like all the other 3D tables, the post-crank idle effort will be interpolated from between these values. So if you have 10% at 10 seconds and then 5% at 20 seconds, if you're at 15 seconds, it'll be 7.5%. Now, whenever this value that's read from the table is greater than 1%, the ECU will not go into closed loop mode. The reason being that the reason why the percentage is there is to cause the engine to flare a little bit and go higher than the target idle speed. So you don't want the ECU to go into closed loop idle in this condition. Now the only other thing that I'd say about the post-crank idle tuning is that sometimes if the engine doesn't want to idle up and you put bigger numbers there and it doesn't seem to flare up the way it should, then it's actually not because of an idle setting problem. It actually might be because the engine's either overfueled because you've got too much cranking fuel in there, or it's underfueled and it needs more post-crank enrichment. So in this case I'd say try 10% more or 10% less in the post-crank enrichment map and see what makes it happier, and that'll help you stabilise on a condition. Now I've just got 2 final settings which are really basic. One of them is the minimum duty cycle. So if the value that the ECU calculates after everything is below this value, it'll be clipped to this value. The reason why we have this is that some idle valves actually become non-monotonic below a certain duty cycle. So for example, 50% you'll get a certain RPM, 40% you get a lower RPM, 30% you get a lower RPM, 25% the RPM is a bit higher, and then 20% it's higher again, up to 0% where it's the same as what it is at 50%. So this obviously makes doing a closed loop control very difficult. So what we do instead is we just allow you to select a minimum where basically above that minimum it has to be a monotonic function. So if the point where the idle speed's minimum is at 30% duty cycle, then you'd enter 30% or 32% or something like that as your minimum. And the last setting is close idle on boost. Now, in theory, if an induction system is well set up, you shouldn't need this, but I've seen this happen on some aftermarket installations, and apparently it's even standard on some factory 1JZ turbo engines, which is where the idle valve actually sources its air from a non-pressurized source. So in most cases, the idle valve will bypass the throttle body, and it's actually called a bypass air control valve by some manufacturers. But in some cases, if the idle valve puts air into the intake manifold, but it actually gets air from the airbox, then that means that when the engine's on boost, then that idle valve actually becomes a boost leak. So if you enable the close idle on boost function, then that will actually close the idle valve as far as possible while the engine's on boost. And in a separate article, we'll talk about closed loop idle control. Thank you very much.